Oh, Harika's trying to fix the microphone. Okay, so hello everyone, and welcome to the what is this? This is the ODE space in WeDoWind, and it's the final presentations for the static your ground truth challenge. So the idea would be that I just give a very brief reminder to everybody about what this challenge actually is about, and then the four speakers just give a presentation and tell us what they've done. And then we have a discussion afterwards. And I think there might be some discussion points about how to upload the results stuff. And then we'll try to make some conclusions about what we've learned as well. And then I'll try and share those learnings on the platform. Regarding all your presentations, I haven't checked actually. Did you all write? I guess I asked you to put your solutions here. So I see Eugenio and Eduardo have got something there. Did everyone else manage it? Juan not.
No, I haven't. Sorry.
You haven't. Okay. So do you have something to present? Would you want to share something on your screen, or you just want to talk?
Yep. Yeah, sure.
I mean, not now. I'm just trying to work out how we're going to do it.
Yeah, for today, yeah.
Okay, fine.
Yeah, yes, I just forgot that part.
No, it doesn't matter. It's fine. So yeah, the original challenge. I mean, this is part of this ODE space which Charlie launched, and he hasn't been able to lead recently because of his what's the word? Career change and location change. They don't have internet in Scotland, right? No. And so I've been trying to keep it running, and so the goal of this challenge, it's called a static your ground truth challenge, and the reason we had it is because we ran a previous challenge on static your misalignment where we didn't have any sort of ground truth at all, and then we realized we found it was quite difficult to come to any conclusions, and so we did our best attempt at trying to get your ground truth data. And so what we did was we have this wind turbine in Switzerland, which is a 6 kilowatt turbine, quite small, but we kind of have control over it, and so we decided to try to set a fixed yaw angle to the controller for a few weeks for each angle. But again, what we didn't do is we didn't actually measure the offset, so we didn't know if there was some static offset additionally to the relative offsets. And so the aim was to look at this data that we provided and predict the offset for a test data set. And the test data set had some yaw periods which were unknown to you. So that's kind of the general idea. And yeah, so maybe we can have a quick presentation of everybody's results and findings now. And I wonder if we can just start with Hannes, because Hannes, you originally did the OpenOA solution, which kind of started off some discussions. Do you want me to just share the description on the screen, or how do you want me to do it?
Yeah, sure. Why not?
So we ended up having yours on this post here, which by the way, I also had the power curves here, which we were discussing. So do you want to just first quickly introduce yourself and then say what you did and what the results were?
Exactly. I'm Hannes. I'm studying electrical engineering, so I'm not native in this space, but I worked for Sarah during this time and collected the data and changed the offset in the control of the turbine. And additionally, I tried to solve this challenge with this OpenOA library, but I struggled a bit to get some useful results. the I couldn't find meaningful result with this library. And yeah,
maybe you can just say something quickly about what these plots are showing.
Yeah. These plots are showing the offset calculated by this library for different wind speeds, and the goal was to, or the goal of this library, I think, is to calculate the wind speed in the, I don't know how it's called, this the time when the wind curve is rising.
Yeah, it's in the like the normal operation period before you get to the rated, isn't it?
Exactly.
Yeah.
And in this time, they take some bins of wind speeds and then lay this curve into it, as I understood it. I don't know if that's correct. And I did this for different labeled offsets, like 0, 4 degrees, and what's below? 6 degrees.
And this, but this one at the top is then the average of, so you've got the 4 different wind speed bins in that area, and then this one at the top is the average of the averages. So is that 7 is the average of these 4?
Exactly.
And so, and that one should be 6 degrees, and that one should be 4 degrees, and that one should be 0.
Yeah.
So that was the
or at
testing.
least the difference.
Yeah.
The difference between, we don't know if there is a static, if there is an absolute offset for all these, but the relative offset between these offsets should be the same.
Yeah, or at least it should be going in the same direction.
Exactly.
So the point is that you're going from 6.9 to 7.9 to 7.0, and
Exactly.
it should be going from 0 to 4 till 6. And then what's this one showing?
Yeah, that's just another attempt out of my own curiosity, because I used in my bachelor thesis the Renzek algorithm to calculate the speed of a robot using the Doppler shift and fitting a sine curve into these points. And I thought maybe that could also, this Renzek algorithm could also work here, because it's really stable against outliers, but also not very successful.
So the result of that was,
yeah, that's around 8.3 degree. I again took some bins, wind speed bins, and fitted in this curve into it. And the red ones are outliers; they are rejected. Exactly, and this is the results over the wind speeds, over this area where the power curve is rising. But again, not very useful data.
so you should be seeing
results.
You should be seeing some sort of, well,
exactly.
It should be lower for blue and highest for green,
yeah.
and in the middle somewhere for orange. But then when we were having a discussion, I think in one of the meetings, we also talked about just looking at the raw data, didn't we? And I think you did I put this in, but because I think you sent it me at some point, but that's like a bin average power curve. Just, it's not even doing any analysis. It's just bin averaging the data from the different labeled sets, right? And somehow it shows that, kind of looks like the controller wasn't doing what we thought it was doing, because it doesn't seem to it should have less power for 6 degrees than 4 degrees.
Yeah.
And that's the raw date, yeah.
It depends on the overall offset.
Yeah.
Yeah.
So yeah, I guess that's. Do you want to say anything else?
No, not.
Anyone want to ask or
Let's
say
see.
anything about this method, or ask Hannes anything?
Can I just check? Are we concluding, Hannes, that from your analysis you couldn't tell which one was which, really?
Exactly. Yeah. I don't know if I maybe wrongly filtered something, but with my attempt I couldn't tell a difference between the data sets.
And is it also true that you didn't submit the results to the folder as at all? Just that because we have a lead. I mean, we have a leaderboard.
Yeah, I think.
Yeah. So
yeah.
yours are not on there, right? Is there 99? Is that a
Yeah,
place? Is that a placeholder?
I think, yeah, I struggled with the folder with you, but I was discussing with Yuri, but somehow this faded, or this discussion, we forgot about this.
Yeah. So what you could do is you could submit I mean, you've got some results, right? They'll be bad, but at least that we have a decent. If we have everything on the leaderboard, it would be nice.
Okay. Yeah, then I have to look with Yuri how we get access.
Well, we can talk about that in a minute because I actually managed to get Harika's result on here by accepting her pull request this morning, and then it appeared. So
Okay.
the process worked. We can talk about it at the end, so everybody can do it correctly. And we probably have to remove this one as well. Okay. Any other questions for Hannes? So does anyone else feel like being the next person to speak?
Maybe us.
Okay.
Yeah.
Great.
Let me then share my screen.
Yeah.
Do you see it?
Yep.
Yep. Okay. Today, Cairo kindly accepted to join us in the presentation. She is my partner in the competition.
Okay.
We have worked. We've been working together like 2 years in rotor side problems, so we are very interested in yaw, static yaw misalignment problems. We didn't get to a solution to present results or to make any prediction of yaw. Normally, the approaches that we use are isolating as much as possible other causes of underperformance. So we just got into a stage in which we analyze data. So they are preliminary results in terms of having a prediction, even if the error was bad. But what we can contribute to this session are the problems that we found on data, things that we found funny or that sometimes it doesn't make much sense. So I will listed here some challenges that we had. Prior to analysis, we already knew that the vein relative 0 point it was not confirmed that the turbine was aligned. So the ground truth, a zeroing ground truth will not necessarily mean that the turbine is facing the wind correctly. However, we have these as references, and 4 degrees and 6 degrees in the ground truth are relative. So we already know that. Also, the absolute wind direction was not available in the data. This is something that we are used to work with directional effects or effects on the layout, like hills around or other obstacles or wakes. And normally when we have the absolute wind direction, we can like outrule filters on data that come from directions that have a high turbulence, and that actually helps a lot cleaning the power curves and cleaning to further analysis. And posterior to analysis, we found three things. The first thing is something that that I mentioned and you just showed, Sarah, is that the performance behavior with respect to the ground truth is unintuitive, because we have seen that in average, the power curve of misalignment of 4 degrees misalignment is below the 6 degrees, which means that that 6 degrees is less misaligned than 4. But on the other side, 0 is above or all. So it is kind of looks like they were swapped, but yeah, we couldn't find an explanation on that. Also, we found a possible malfunction of the yaw controller. So I will show you afterwards. And the power ranges per wind speed are too wide. So this is a bit description of how was the data cleaning. We worked only with data between the cut-in and rated wind speed ranges, just to, because outside those ranges, it used to be, there are more factors that affect like the pitch control and more noise. And also we resampled the data to 3 seconds because of these strange peaks when we get the relative wind direction histogram. What we have got is that these strange peaks of high frequency directions were exactly a -2 degrees, -12, and -24, or around that. I don't know why, but they are like outliers. They are very isolated, and just by averaging by 3 degrees, it just got a smoother distribution. So the first thing that we found was the power curves as similar. It's exactly the same power curve that you showed before, Sarah, in which it looks like 4 degrees of misalignment. It looks more misaligned than 6 degrees. And we might find that this is funny or somehow strange, but at the end, when we plot the raw data, we notice that there are the ranges per wind speed are very wide. So if you, for example, focus on 4 meters per second, you actually have like a range from 1 megawatt to 6 megawatts, which is something that it is not common when we perform analysis. And this may suggest that there is another problem of performance. All the points here below on the range, knowing that we have, the metadata says that the rated wind speed of this model is 7 meters per second, but like empirically we find that it gets the rated power like at like 4, a bit more than 4. We should know, we could have ignored that at the beginning, but now that we check that these wide ranges, it is like regardless of the ground truth, if it is whether 4 or 6 degrees or misalignment, looks like there is another source of underperformance that may mask the static yaw misalignment, that may explain why this power below appears. And well, the fact that this curve looks a bit thinner is just because it has less data. But yeah, I don't know if you guys disagree. By the way, you can interrupt me at any moment if you have any comments. But yeah, it is difficult to isolate things when we have these ranges so thick. And the second thing about the relative wind direction, the relative wind direction in normal operation, we see when we plot the histograms of all of it across the 10 months of testing, or we expected that we had like the mode or the peak of this histogram was in 0, because the idea is that the controller will also follow the 0 error, the 0 relative wind direction. So we found it really funny why that happened. It is kind of aligned. The mode is like at -10 degrees. And actually, something that caught my attention from harness solution was that the predictions were around this same value, like I8. So might be responding to this strange misalignment that actually with Carol, we tried to figure out why will something like that happen. We have some hypotheses, but they are related on problems in the control, physical problems on the controller. And if we separate this distribution per U offset, and we found that they are kind of aligned. So regardless of the U offset, the yaw misalignment, the ground truth, they are like shifted towards the same side at the same quantity. And okay, we calculated the central tendency, which is basically the average mean. Rather than getting the peak of the histogram, we got the average mean, which may suggest where we can divide each of these distributions half by half. So if we see that the point that this point is always seems always to be right to the mode of those distributions, might be because of a heavy tail effect here. And either way, it looks like they are very similar, 0 minus 8.14, around -8 degrees. And the only difference is at 6, that was a little smaller, but it might be just like no statistically significant, this difference. So that means that we already have, beside the problem, the problem of the wide ranges of power per wind speed, we have that the controller has problems to actually face the 0 point for some reason that we don't know, and that also definitely may excuse or results if we want to predict yaw misalignment. So okay, now I applied this same weighted average, but now I make a differentiation per wind speed. So it is like, imagine this point, each point here is, I just filter out 3 meters per second, and for each of the histograms that resulted, I calculated the central tendency. And that's the only way we see that there is a change of it. Like if you see an average, looks like they are similar, but with higher wind speeds, they kind of separate themselves. This is the most informative thing, like the most discriminative thing that we found about the differentiation, to differentiate the different offsets. But we couldn't go further than that. No, we don't have ideas on how to apply this to a solution that can classify those offsets. And finally, this is something that Carol found recently, the wind speed per blade pitch. By the way, we filter everything in the state 10, which is normal operation, but this data here doesn't correspond to normal operation. And I think, I'm not sure, Carol, do you want to add something about it? Hello.
Yeah, sure. Yes. So as Juan said there, this pitch behavior is obviously not normal at all, especially in where it is there in the kind of 0 to 5 range, which is between cut-in and rated power. That's obviously not normal pitch behavior. So I expected to see that pitch behavior correspond with the large spread on the power curves. You know, the basically underperformance impacting the power curve. But it actually was not at all related. In fact, if you look at plot the same the points that are massive outliers above the pitch there actually correspond with better power performance on the power curve. This appears to be widespread sensor issues. And when I dug into it, I also found that in the same periods that we have those massive pitch outliers, there are also major issues with the generator speed. But this isn't like it's not a period of time in which like a sensor was wrong or anything like that, which would sort of, I guess, would be the expected thing to find next. It's just intermittently throughout each month since, I believe, March. Just sometimes the generator speed appears to be way lower than it should be, or appears to be way lower, and the pitch appears to be way higher, but then they're not actually translating into the type of physical phenomena you'd expect to see on the power curve. If you don't, I could share my screen for a moment here. I can illustrate. Sorry, my laptop's going a little bit slowly, but I'll try and share here.
It's coming slowly.
Great.
Oh yeah, it's worked here.
Yes. So you can see here, this is the same graph one was sharing a moment ago, but color coded. The graph on the left is color coded by generator speed, and then on the right is colored by power output. So the generator speed is basically the only thing that comes even close to explaining this big group, bunch of outliers here. But then what we're actually seeing in terms of power is it is reaching up to, near, even with that, it is still reaching near its rated capacity. And also then, I thought, well, I found a candidate. I will just simply rule out these low generator speeds, and then that will tidy up my power curve and make my power curve usable. But even doing so, these low generator speeds don't correspond with the low performance either. So even having found this, it's literally just a sensor issue that's somehow impacting both generator speed and pitch, but not in the same way. It's making generator speed appear lower, pitch appear higher, and then actually having no noticeable impact on the power curve at all. And to just further illustrate, I guess, the fact that this is a sensor issue. So this is a graph of generator speed on Y and power output on X, and the reverse, power output and generator speed. Either way, that you can see here, power output up to nearly 6 kilowatts, which is just below rated capacity, associated with generator speeds of only 57, when at that that power output should require the generator to be turning at 700 RPM. And just to, again, further illustrate, this is what those graphs look like on a normal turbine, our normal data set is, fully continuous there, and we don't have this this spike here or the along there. And this is also, by the way, I've already filtered out the the stops here. So
you know what? I'm just sorry to interrupt. I'm just thinking about something, Hannah. So I don't know whether you can confirm this or you know more about it. We don't really know much about how our own wind turbine works, right? So all this analysis is kind of showing we don't actually know what happened when we set this yaw angle to a given angle. We don't actually know what processes it actually set off. But the things that you're talking about are things that are independent of that, right? Like this is not just, this is including the zero offset.
yes,
This has nothing to do with us changing the offset. I'm actually wondering if this wind turbine has got two generators. Two at a low speed and a high speed one, and it switches between the two at a certain speed. And we didn't know that, but maybe it does. I don't know, Hannes. Do you know that? Hannes has worked most with his wind turbine.
Actually, I'm not sure.
Like in the
But
description
maybe
that
I
we've got
checked
about
the
it.
menu.
Yeah, I mean, in the description that we've got online about it, it doesn't say that. Like in the official, description of how the wind turbine works, it doesn't. It just says it's got a variable speed. It says it's got a generator. But I don't
yeah.
know. This data is making me feel like it might have two, and we didn't realize.
Well, we're also not, as I said, it's across all power ranges, it's across all wind speed ranges.
Yeah. Okay, so maybe not.
It's not, isolated in a specific time. I really think it's just a sensor issue, because
Yeah.
if it was an actual physical phenomenon, it would be reflected on the power curve, which it's not. So I suppose in conclusion, there is, some quite substantial issues with the data set itself.
Yeah.
But the main thing, I suppose, is what Juan mentioned earlier. It's that the power curve has such an enormous spread of values in each wind speed bin, well beyond what's actually physically, possible during normal operation, which it basically means that there's either some form of curtailment or limitation that's happening on the turbine that's not being captured by the any of the status columns, because it is, as I said, we've filtered all to the normal operation. So either there is some form of a limitation going on that's simply not being captured, or else there is some other underperformance on this turbine that is just enormous in magnitude compared to the induced underperformance associated with the yaw offset. And it's just so drastically overshadowing that the impact of the yaw offset that it's making it pretty much impossible to determine what see the impact of the yaw offset on any of the other variables.
Maybe just one question before we have to go to other people at some point. But just the only thing we know about is that between 5 and 6 p.m. in certain times of the year, they have to curtail or even shut down. I'm not even sure, because of flicker. But that, I don't think that's not the problem, is it? Because that would be recorded as one of these turbine status numbers, I guess. And
it certainly should be recorded as a status, yes. But also that usually shadow is a stop rather than a curtailment.
Yeah.
So I'm not sure if you could maybe confirm which it is.
Yeah. I don't know whether Hannes knows. Actually, those turbine status codes, we actually have an ontology published, which is describing what those status codes are. So I should be able to find them. But we do know what those codes even mean. So I can check that. But I
can search them. I think I sent it once to Yuri, so I have it somewhere.
Yeah, I mean, we have it on the, on the Techno portal, we've got the status and alarm
Okay.
codes. I just have to find it as well. Did you, I mean, this is really, really interesting, definitely for us. Do you have anything more you wanted to say, Juan and Kira?
No, just basically these are the reasons why we couldn't go further. Well,
Yeah.
we still believe like having the correct cleaning of the data and isolating the sources of underperformance, we can get a good prediction with the maximum point capture algorithm. But yeah, that's the tricky part. That's the problem. We have to correct for wind speed because we know that wind speed is affected. And also, yeah, this outrule every other problem before we go to this analysis.
Well, thank you for finding out so many interesting things about the operation of our turbine. I think we definitely, I mean, we basically need to look into that. And it's, I mean, we thought, okay, the yaw control, we don't know what's going on when we set the yaw angle. And this is obviously some sort of weird thing going on. But now what you've shown us is really some general thing that's happening with the wind turbine that we never really looked into in that much detail. So that's very interesting for us. We're definitely going to follow up on that. I was wondering if you to save effort, what you could do is just in your report template, if you just want to put a link to that document that you were presenting from, like you don't need to do anything more than that. You can just put a link, or you can copy and paste it, or whatever's easiest for you.
Okay, yeah, sure. I can push it or to GitHub and give the link, or I will see what is easier for me to get the description, and also I will unify with Carol's findings as well. Yeah.
Great, thank you. So let's move on to the others because we've got 19 minutes left.
Okay.
I don't know, Eduardo maybe, because I don't know if Harika solved her microphone problem or not. Or maybe we can just, Harika, you can just say quickly so we can, and we know we have
can you
solved
hear
it.
me?
Yeah.
Can you hear me? I'm so sorry,
Yes.
like my Teams is not a great friend. It just keeps troubling me now and then. Hi everyone. This is Harika, and this is my first time joining any WeDoWind challenge, and I really find this community quite helpful in understanding, especially the turbine operability. So my background is more in designing rotor blades and everything. So I'm trying to venture more into this segment to understand how the final operations basically look like and what is expected out of the design parameters. So this is my first attempt to solving such kind of data set. So instead of looking more, I mean, I really liked what the Yuan and the co-team member presented. It was a lot of information, and I didn't know that's the good way, a very great approach to look how to relate this basically to the turbine operability. But my attempt is kind of very similar to what Hans did, but at the same time, when I used the OpenAO method, I could see that it was not really fitting the curve properly, and it was not really showing any trend, and the data kind of didn't make real sense to me. So basically and also when I was looking at the challenge, I can see that your 4 degrees. Thank you, Sarah. I was just about to ask you if you could just share my results. So what I started doing initially is basically to look at the data, what I had on hand, and to see where exactly the signal was. And as soon as it hits the rated speed, basically it was not really showing much. And when I look at the misalignment, basically shows approximately like a consistent 13% power deficit across the every wind speed binning for a 1 hour wind speed binning. And then I could see like there was basically the seasonal compound effect also, as I think yaw is basically measured around summer and the rest in the winter, like 0 degrees and 4 degrees. And then I went further to just run the OpenAO model to see how it is basically showing the results. And as I mentioned, it was very hard to understand the binding data, and especially to find a trend. And then basically what I did is like I used the physics method where you basically put the power law, and I can see like there was a bit of an overlap, but there was a asymmetric distribution of the power curves. So I took these feature lines and then instead of going for a symmetric distribution like a power fit, what I did is in my next like the asymmetric cosine formulation, I chose where the peak value is there, and then basically I've tried to fit the left exponent and then the right exponent to figure out the real value based on your directly related features. And then even without without any power fitting, I could, when I overlapped all these results in the histogram, I could see that there was an overlap and then there was this asymmetricity. So I, instead of cleaning or like really trying to go on grunt with the available data, I tried my attempt in understanding the cleaned data and what basically I could actually find out of it. So that's the attempt I made, and I'm still kind of learning around this. So yeah, if you have any questions, I'll make an attempt to answer them.
Okay, sounds good. Thank you. Questions?
You were successful in detecting which class of which value. I saw the confusion matrix, and one of them is very high, like the accuracy.
Yeah, I think
0. Okay, yeah.
Yeah, and I think like even with the earlier power curves, what I could see is you could still detect like a 4-degree, but then the 0-degree and 6-degree had a very little power. Like they were on such an overlap, it was getting really difficult to actually kind of differentiate between both the values, or like both the data points. So that is something which yeah, I'm not 100% sure of, but I could see like I was able to differentiate the 4 degrees yaw.
Okay. Yeah. Okay, yeah. So thank you.
Thank you.
Okay, let's do Eduardo then. So we actually managed to get everybody's presentations, and then hopefully we'll have a few minutes at the end to finalize, to discuss more. Eduardo, do you want to share something yourself, or shall I share?
Yes. So good afternoon. I think it's in Europe. Here in Brazil, it's good morning yet. So
Hopefully not too early.
just to introduce, I don't know, are you seeing the screen?
Yeah.
Okay, just to introduce myself and Eugenio. Eugenio was unable to be here with you, so he sent me. My name is Eduardo. I'm from the Federal University of Santa Maria in the southern region of Brazil. And so we have developed a solution to the challenge, and different from the other participants, we used the first version of the data set because we made this analysis a long time ago. I'm just here to share the results we got. So we basically compared two algorithms. The first one's the OpenAway that Hannes and Harika showed us the results. And we also applied the UFSM algorithm, that is an algorithm we are developing in a R&D project that we are running here in the UFSM. And basically, the OpenAway process the data applying MAD. It's based on cosine curve. And the UFSM R&D algorithm is processed using local outlier factor. It's based on the power curve and does not account for the cosine curve. So what we've done to analyze the data sets, we basically resample the data. That was an Eugenio idea because we didn't get good results with 1 Hertz data set. So we resample the data for 30 seconds, 1 minute, 2 minutes, and 3 minutes. We also tried to 10 minutes, but we understood that it was not too many data to have a good analysis. And then we applied the before and after misaligned data set. This data set is the one that is 0 misalignment, and then we have the 6 offset, and compared the results by both algorithms. So using the algorithm that we are improving, we got some results closer to the 6 degrees offset. So for 30 seconds, 2 minutes, and 3 minutes, we have some similar to 4 degrees of difference, the before and after data sets. And when we go to the OpenOA, we have a good result at the 1 minute sampling with minus 5.4, this offset detected by the OpenOA. And here, just to say that theoretically, I don't remember exactly how we configure, but I am quite sure that in this case, we just use the same parameters that are in the document of the OpenOA. We didn't work on the explainability of the results or the algorithms. We just ran the OpenOA, and we got this result for these different data sets. I am not I am not sure if the explainability of this good result is only because of the data sampling of 1 minute. But anyway, that was the results we got for the OpenOA. Here I plot I have the plot of after the yaw offset, and then the before yaw offset, and then after the yaw offset. What we have of conclusions about the OpenOA, not only for this challenge, but also in other data set that we have applied the OpenOA, it's that it's a little bit sensitive to the parameters. So if we change the wind speed range or the wind speed range bins and any other parameter that it has, the results may change a little bit. Basically, just a long short history. This is the contact of me and Eugenio. So if you want to reach out, we can work on our codes just to make it available for you also. So anyway, that's all.
Thank you. Did you submit your results for the test data set?
I don't think so. Yeah, because Eugenio just reached me, said let's present our results like 1 week ago. So I think we didn't submit.
So maybe I can just quickly tell you what you can do. Or has anyone got any content related questions first, and I can tell everybody the same thing about submitting the results. Does anyone want to ask Eduardo anything about the method? John, you're muted. Your mouth's moving, but no sound's coming in.
The only thing that confused me was the you talked about using the 2 different methods, OpenOA and your UFSM method.
Yeah.
And I wasn't quite sure the difference between the results, whether that you talked about those different deltas there. Was that to do with the UFSM result, or was that the OpenOA result?
Sorry, I didn't understand exactly.
Sorry, yeah, your results.
Okay.
Were they based using the OpenOA method or based on using your UFSM method?
The OpenOA.
Well, this table here.
Yeah.
The results in this report Eugenio posted is not the same because I found a little error in the code. But...
Okay. So do you have? So I guess John's question is kind of going into the same direction as my question as well. So what, if you can, what would be great is to have a submission of the results for both methods for the test.
Okay.
For the test data set. So we had the training data set where you knew what the offset was, right? But we actually, in the data set, there's a test set as well, which doesn't have the yaw the yaw misalignment labeled, and the idea is that you submit your prediction. I mean, you can do it 6 times. You can do it once for each sampling rate, and you can do it for the OpenOA, and you can do it for your method. And just so that we can, I mean, it doesn't really matter because it's not really a competition, but we made this leaderboard when it would be nice if we had, at the moment, we've got two results on it. So 99 is just our placeholder, but I think 10 and 12 are Hannes and Harika, and it calculates the error between whatever you submitted and the actual value. And then we can at least have some result which we can, if we have, I think if Hannes and I think Juan can't do it because he didn't have any results, but I think at least if Hannes and Eugenio or Eduardo could submit that. There's instructions on the WeDoWind page. You actually have to go to this GitHub page, and you have it it tells you how to do it, but you have to add a branch, and then it does an automated check. And actually, if you can tell me when you've done that, I can merge it. I have to accept your fork and merge it, and then as soon as I do that, it appears on the leaderboard, and then we can at least have a summary of the results. Is it
okay? We will work on it. Yeah,
and then as well, if you can, I think you've got, if you maybe correct anything that might be wrong, you need to update in that report. And as I said, Juan, if you can put something in there, even if it's just a link, that would be great. And then I'll make some summary, like I'll summarize the solutions like in a blog article or something. I mean, maybe if we can just come to the conclusion. So what I've concluded is that our wind turbine's doing something strange. And it's very interesting to try to work out what. The yaw angle that we set seems to be, it seems to be the case that the 4 degrees one led to lower performance than the 6 degrees one, but because there's quite a massive spread of data, it's very difficult to actually work out the answer. I guess we've kind of concluded that OpenOA is extremely sensitive to sort of outliers or any dependencies on wind speed, and that it doesn't necessarily work very well. So that kind of what I heard from you all. Anyone else have any sort of final discussion points or takeaways that we should be taking out of this? Oh, Harika, we can see your face now. Nice to see you.
Hi, everyone. Nice to meet you all.
Any sort of observations or comments?
Yeah, I mean, I just say, obviously, I've attended in my role on the board of directors to see one of these challenges in action and get a bit of a feel for what's going on and so on. So for me, it's been enlightening to see what it is, and it's probably worth a conversation after, Sarah, in terms of where we've got the results and what you're getting from your turbine and so on to see how this works out. Yeah.
Yeah.
I'm intrigued to see what Charlie's thinking, actually.
Yeah, well, I'm interested in that.
I'm wondering whether we've just got an artificial photo in front of a webcam somewhere that he's shaking, that he's got set up to shake regularly.
He's smiling.
Yeah, it's real. Can you hear me?
Yeah.
Yeah.
Yeah. No, I think this is really interesting. I guess we haven't managed to solve the problem that we wanted to solve, which is around the static yaw misalignments and identifying them. But I think all of the analyses are really interesting and showing different issues or problems with determining something like static yaw misalignments. So like if even that bit around, the sampling frequencies, it's very odd that you get hugely different results just based on whether you're sampling on 1 second, 30 seconds, 1 minute, 3 minutes, because that shouldn't be something that really affects the end result. And it's very interesting to see like the control side of things, like what is that generating speed doing? It doesn't make much sense at all. And so it shows how important it is to really understand what your machine's doing and filter the correct data to be able to use it in kind of detailed analyses.
Yeah.
So I think it's like, I think what it shows is how complicated these kind of data analysis challenges are, even when we've got a control system where we're like, well, we can do anything we want to this turbine and adjust the parameters, and we should be at a ground truth. But yeah, it turns out it's, again, not that simple.
Yeah. Yeah.
It makes me wonder as well, given the problems with static yaw misalignment there are in the industry, makes me wonder how the OEMs do it and get the reliable numbers out of it.
Well, so
Yeah.
what I put on my screen and in the chat is I mean, I guess probably you all know, and maybe you're all signed up for it already, I'm not sure, but we've got this Nadara Yaw Misalignment Challenge running, which it launched in April, and they've actually got some real ground truth data. So they put a measurement device on some of their turbines, and they've got data of nearby turbines as well. And so we've created actually two leaderboards. So one of them is just using the metric for how well can you predict the yaw misalignment for the test data, but we've also tried to include it with like the costs that you would save. So for example, if you use a physics-based method, which I'm really interested in how well it works, because if you use a physics-based method and you can make sure it works, you don't need to make any measurements at all. Whereas if the more training your method needs, the more measurements Nadara will have to do, and the more it will cost them to make the measurements. And so we've tried to create a metric which now reflects the type of method and the costs saved, and I think that's also could be really interesting. So for me, it's kind of a natural progression from this challenge to go on to that one where the database is maybe a little bit more stable and there's more data. Although I have to say, in the interim presentation last week, we noticed there's quite a lot of difficulties with the data as well. So maybe Kiro and Kwame, you'll be, if you apply some of the techniques you use for our data set to theirs, you'll find some interesting things about the way the Nadara turbines are running, but you're not allowed to work out what the manufacturer type is because it's been anonymized. So yeah, I guess it's 1 minute past, so we should stop. But thanks to everyone for taking part in this. Yeah, and I mean, yeah, we didn't find an answer like we were expecting, but all this work and these discussions and the analysis helps us learn. So I hope it was useful. I will be making a summary for you. I'll wait until you finish submitting the things to do that. Maybe we can submit an out of conference abstract or something. I was thinking just kind of with the main learnings, and so I will contact you separately asking if you want to be a part of that or not. I'll probably send you a short feedback form for you to fill out and tell us about your experience of taking part in the challenge as well. Yeah, and otherwise I hope to see you all in other challenges. I know Eugenio is coming to the event in person next week. So next week on Thursday we're actually running a workshop for the Nadara Yaw Misalignment Challenge, which you can still join if you haven't joined it yet. Yeah, so thanks everybody, and see you all soon.
Thanks. Bye.
Thank you.
All right, bye everyone.
Bye.
Thank you.
Thank you. Bye.
Thank you. Goodbye.
Bye.